Oh my god, I have a logistics test tomorrow and I have no idea what any of this is. The growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dp over dt. What the heck does that even mean? I don't understand any of this. Ugh. Alright, I'm just gonna watch Weekend Update.
Weekend Update with Seth Meyers.
And here are tonight's top stories.
Hello and welcome to the 426 News. I'm your anchor, Chris P. Bacon. Our top story today, NASA sends probe to Uranus. People everywhere giggle. In a recent survey, 9 out of 10 Americans say that 1 out of every 10 Americans will disagree with the other 9. Another top story is an inappropriate time to use sarcasm. We have received the last words of a man stabbed as someone entered his home, and the quote is, "What are you gonna do? Stab me?" Learn from his mistakes. Putin decides to stop being evil and give everyone in Russia free ponies. Scratch that, an intern was just fired. Onto the political front, we have recently taken a poll of students from the ages of 18 to 24 across the nation, and only 11% believe that Donald Trump will serve as a better president than a potato could. They're afraid of a World War III. Going along the political lines, we have a gripping race ahead of us with Hillary Clinton, Bernie Sanders, and one of Willy Wonka's missing Oompa Loompas. This just in. One second. Oh, it seems that the world outside is being overrun by rabbits because there's no population control. And now on to sports with Molly Kuehl.
Thank you, Chris. As the rabbits worldwide are reproducing at an alarming rate without limitation, they have made their way into sports. Unfortunately, as the balls. Now on to our mathematician, Rational Ryan, to explain why this is improbable.
Well, hello there. I'm Rational Ryan, and I'm going to explain to you why logistics is an important part of today's society. Okay, in terms of logistics, it is similar to an exponential curve. However, there's one slight difference. So, to start off with an exponential curve, you have the equation dp over dt equals kp for some k that is greater than 0. Now, if we want the growth rate to approach 0, which is the case for a logistic differential curve because there's a maximum carrying capacity, then we need to introduce the limiting factor of m minus p, which leaves us with the equation dp over dt equals kp times the quantity m minus p. This allows you to have your rate of growth approach 0 at one point and ultimately hit your carrying capacity. The curve for such a function would look something along the lines of this. Now, there are two very important things to note about this graph. The first thing is that there is a horizontal asymptote as the growth rate approaches 0. The second thing is that at the very center, halfway between 0 and the carrying capacity, is the fastest rate of growth and also the point of inflection. Now you have a function that looks like this, where you have your horizontal asymptote at your carrying capacity p, and then your point of inflection and the fastest rate of growth exactly halfway between 0 and the carrying capacity. Now, since we're talking about population control, what happens above this horizontal asymptote? In this area, the function actually experiences exponential decay that once again flows towards the carrying capacity k. Now you have a function that looks something like this,
with your carrying capacity P and your point of inflection directly between 0 and the carrying capacity. Now, the real question is, since we're talking about population control, what happens if you have too much of a population? Now, in this area above the asymptote, a function will actually experience exponential decay until it reaches the asymptote and the carrying capacity P of the population. So this carrying capacity, this asymptote and dotted line represented on this graph, is extremely important to a logistic function because that's what differentiates it from simple exponential growth. This asymptote is the maximum amount of whatever population nature can physically sustain, whether it's natural resources, space for living, and oftentimes a question will ask you, why is the population only able to hold 6,000? What would happen if there were 7,000? To explain why populations have a limitation, we're going to run through a basic example problem. Now, in this problem, the growth rate of a population P of bunnies in a newly established park is modeled by the differential equation dp dt equals 0.008 p times the quantity 100 minus p, where t is measured in years. So let's go through part A. What is the carrying capacity for bunnies in this park? Part A. What is the carrying capacity for bunnies in this park? Well, with our differential equation, dp over dt equals 0.008 p times the quantity 100 minus p, we can tell that since the limiting factor here added to change it into a logistic growth function is 100 minus p, 100 is our m, or our carrying capacity. So our carrying capacity equals 100 bunnies. Now, what is the bunny population when the population is growing at the fastest? We know that exactly halfway between 0 and the carrying capacity is when the rate of growth is the fastest. So in this case, our population is growing the fastest when it is 50 bunnies. So for part C, what is the rate of change of the population when it is growing the fastest? This is very simple, as you simply plug 50 when it is growing the fastest into the differential equation that we had looked at before. When you solve it out, you end up with 20 bunnies per year as the rate of change of the population when it's growing at its fastest rate. Now comes the longest and often most difficult part of any logistic growth problem. So part D is to solve the differential equation with the initial condition that p of 0 equals 6. Oftentimes, you will see a slope field attached to this type of problem, and you will have to simply plot the point 0.6 in the slope field and then create a logistic growth function based off of the slopes that you're given. So in this case, you start off with dp over dt equals 0.008 p times the quantity 100 minus p. So the first step of any differential equation problem is to separate the variables, which you ends up with dp over p times 100 minus p equals 0.008 dt. Now you can integrate both sides. So you have the antiderivative of each side. Now for the left side, you need to use partial fraction decomposition for a of p plus b over 100 minus p. So when you solve this out, you get that a equals 0.01 and b also equals 0.01. Now to make this equation easier, we multiplied both sides by 100 to simply get to better numbers to deal with. So the equation we have right now after our partial fraction decomposition, multiplication of 100, and taking the antiderivative of the left side is the natural log of p minus the natural log of 100 minus p equals 0.8t plus c. So you can figure out that the natural log of 100 minus p minus the natural log of p equals negative 0.8t minus c to make our lives easier in the upcoming steps. So the natural log of 100 minus p over p equals negative 0.8t minus c. Now that we have e to the negative c equals 15.67, we can switch that in as a multiplier in front of e to the negative 0.8t. It would be a negative 15.67 because it is a subtraction between the point 8t and the negative c, but since it was 1 minus that quantity, we can simply make it 1 plus 15.67 e to the negative 0.8t. After multiplying both sides by p and then dividing by the quantity 1 plus 15.67 e to the negative 0.8t, you finally end up with your equation for your population, p equals 100 divided by 1 plus 15.67 e to the negative 0.8t.
Whoa, that was some weird dream, but I get logistics now. I think I'm gonna pass this test. Alright, now I can go back to sleep.
Hello, welcome to the 723 News. I'm your host, Arthur Anymore Donuts. Hello, and welcome to the 514 News. I'm your anchor, Thor Buttock. Hello, welcome to the 326 News. I'm your anchor, Frank and Stein. Hello, welcome to the 837 News. I will be your anchor, Brock and a Hard Place. Hello, welcome to the 915 News. I'm your anchor, frankly, I don't give a damn. Hello, and welcome to the 124.9 hike